So the first thing I want to point out is our exam is whatever it is, Thursday. I did go through and update the overview of the exam. I don't know if you noticed that, but I was going to post an announcement about it, and then I wanted to finish some other stuff, and then never bothered to post the announcement. We've got some numbers. Guess what those numbers mean?
That many questions?
Ballpark that many questions. Okay. As far as length of the exam, there's 30 multiple choice and 8 short answer, I think is how it breaks down. Yeah, I think that's right. And what I went through and did was roughly said to answer this question, you would need to know this topic, you would need to know this topic, and then I listed those along here. This kind of totaling for the number of questions is not going to perfectly align out to, oh, that says 10. Oh, less than 10. So I think it's 8. Some questions require content from multiple areas, so some things get double counted. Okay, so you could see more things appear in certain areas just because you need to know multiple content areas to answer that question. And then the other part is that when those numbers were put in, I had 25 short answer questions, multiple choice questions. And in looking at how points distributed, I felt that overvalued then each of the multiple choice questions. So it's kind of a delicate balance between, do we have lots and lots and lots of questions, or do we have only one question? Lots of questions, you could get lots wrong and not have it affect your grade as much. With one question, you get it wrong, it could affect your grade a lot. So trying to find that balance for me usually kind of hovers in the 30 to 40 question range, total question range. And so that's where it ended up coming out, is that I decided that 30 multiple choice made the most sense to get us to our 100 points, keeping each multiple choice at 2 questions, and then the show your work varying in point value. So those 5 last questions, again, I didn't have going into this list because I was at a loss of what questions to put in and how to write them and format them and all of that fun stuff. Okay. So those questions didn't get added to this list. I did try to keep them more on the simpler aspect for those new 5 questions, but simpler in my mind doesn't necessarily translate. Okay, but that was the intent. Okay. Order, there is no order at anything as far as how the questions are organized within the exam. It's really just organized to reduce page content or the amount of pages as much as possible. Okay. So don't be starting your test with necessarily the very first question or the very last question, because you don't know which one is easier or harder. Okay? And for everybody's going to know the content to differing extents. Some people are awesome with nomenclature. Some people, like me, are awful at it and would try to avoid it as much as possible. Kind of makes sense? So what you need to be doing when you start the test is find the questions that make the most sense to you and move through to those. Okay. I will add that reading the directions is useful. So I would recommend reading the directions. So when you get the exam, you can write your name, read the directions, and then flip through the exam to get a feel for where everything's at. Okay. Yeah. And the reason for kind of doing that is it helps establish that feel, and it also reduces anxiety. Almost everybody is high energy as the exam first comes out, and so you increase the odds of making a mistake right away. So if you can kind of delay and reduce some of that anxiety by just reading, that can calm your nerves enough that you answer more appropriately as the answers pop up. Make sense? And then I guess the last thing that I'll say about it is typically when I build a multiple choice exam, I go through, build the key, and then make sure there's a nice, perfect, even balance of all your answer choices. So there's no one preference over another as far as answers go. I have not done that at all for this. I honestly do not know how the answers will stack out. I'm hoping not all of them are the same answer choice, but I honestly don't know. Well, actually, I do know a little bit. I know I've mixed some of it up, but I don't know beyond that. So you could see an overwhelming answer choice of A, B, C, or D in any one of those categories, so don't let that panic you. Like I said, I try to disperse it more evenly. Okay? You kind of made a face at that. Proper test building should have an even balance of all those answer choices. So if someone just says, I'm just going to guess C all the way through, that person doesn't necessarily have a higher or lower score for that matter than what they should have had for just blind guessing. Okay? So it's just good test design. Yeah, and I think it's a fairly decent spread for what we've talked through. So I think it's okay. I think it's weighted appropriately for what we've dealt with. Questions about the exam?
What are the short answers? Is it explaining something?
Explaining, sometimes it's drawing, that I want to see how you draw an individual structure, how you convert the name to a drawing, that kind of stuff. So that drawing part of the class is what I'm expecting you to do. That's what would show up in there. Some of it can be explaining why is this higher or lower in energy, because we've talked about some energetic stuff. In the future, it'll be why is this product formed over this one? Show me how this reaction happens using curved arrows. Okay? None of that is stuff we can test on now, so for the most part, it's draw this. Show me that you know how to draw and put that together. Make sense? Before class started, a couple people were kind of nervous about dealing with our isomers and identifying those relationships. For the most part, it's just something that you have to know, right? Because they're definitions of those relationships between those structures. So you would pick that up by practicing, and that's why you see a bunch of practice in active, and why, if that's not enough for you, you should go find some more, identify those relationships. Okay? There are a couple different stages of identifying relationships. This is the first one, I would argue, is our simple identifying our stages, and we've got an example question from active that we can look at here. While the question is kind of removed from view, it's asking which of the following are isomers of each other. So what they're asking you to do is effectively move through this flowchart. So what we would do is compare structures, let's say 1 and 2. Okay, so the first thing we would ask is, do they have the same molecular formula? Okay, this is where, if we're really fluid with looking at our drawings and understanding what they show, we can get to those formulas pretty darn swiftly. So do they have the same molecular formula?
They both have 7 carbons.
Okay, so they're both C7s.
But then the number 1 is going to have 4 CH3s.
Okay,
Number.
so it's a good way to chunk it. We have 4 CH3s, which as a number would be 12. 12 hydrogens, 4 CH3s, 4 times 3, right? 12. What else do we see?
On the right one, it's only going to have 3 CH3s.
Why would I balk?
Whoa.
Why would I balk? Why would I say, why are you looking at 2?
I thought you were comparing 1 and 2.
We're comparing 1 and 2. Why are you jumping to 2? Have you compared 1 yet? You're saying it has 4 CH3s. Take a look at the blue dot. Does that have its octet shown?
No,
No, which means
it's a CH.
there's another hydrogen there.
Yeah.
So I don't care that there's CH3s. I care that there's 3 hydrogens. There's 4 sets of those, which means there's 12, which then means I also would have to consider the blue hydrogens.
So we're counting hydrogens.
Why are we counting hydrogens? What are we trying to find? What was MF?
Molecular formula.
Molecular formula. So how many atoms, which atoms, and how many are present? So what we're trying to do is come up with that total. and that purple one has 2 hydrogens. So if we go through and look at structure 1, we have 12, 2, and 2, which gets us 16 hydrogens. How about structure 2? You're correct to try and chunk, so we could say we have 3 CH3s.
Yep.
3 CH3s is how many hydrogens? 9. Now what else do you see?
There's going to be 3 CH2s
I agree with that. I would try and move to the next one. There's 3 CH2s.
and 1 just H.
I understand where you're going, but let's finish the CH2s. If we have 3 CH2s, how many hydrogens is that? 6. And then we have the one just H. How many how many hydrogens do we now have? 16. So if we think back to why I balked earlier on, you went through and said, well, I have 3 CH3s and I don't have that over here. Effectively saying you don't have the same molecular formula and they're the same molecular formula. Okay? So when we're talking about molecular formulas, we can change the different bonding patterns. This is why we have to be fairly fluid, counting our atoms, getting to at least ballpark formulas pretty swiftly to be able to understand those. And we'll see a shortcut here in a second. It doesn't require quite as much counting. Okay? So they do have the same molecular formula. Okay? So that's where we would move to yes. We're still at our A and B structure, but now the question we want to ask is, are they superimposable? Is there any orientation that I could move those molecules? Remember, those are all sigma bonds. Could I rotate those sigma bonds so that structure 1 could superimpose on top of structure 2? Okay? That is very challenging to do. Okay? But you're right, you can't do that. What we could try and do is just pick our carbons. So we've got this carbon chain, right? Pick our longest carbon chain. And we want to superimpose that. In the first one, it's 5, and the second one is 1, 2, 3, 4, 5, 6. Literally, the carbon chains can't overlap because one has 5 carbons, one has 6 carbons in that chain, which means they are not superimposable. Okay? There's no way I could superimpose them, which then means they are isomers. Could I dig deeper? Yes. Okay? Do I need to for the question? No. Do we need to for your sake? Yes. Okay. So now what we'll do is look at the same atom connectivity. This one is kind of a cheat for us. Do they have the same atom connectivity? One had a 5-carbon backbone, the other one had a 6-carbon backbone. They very clearly have different atom connectivity, because if it was the same, we would have 5 and 5. Okay? So the atom connectivity is different, which means the relationship between them is that they are structural isomers. Okay? The structural isomer category is a bit of an obnoxious one because there's a lot of different, well, there's 2 names that I can think of off the top of my head. Structural isomers and constitutional isomers. Okay? They're both referencing the same thing. So what we've done is just kind of moved through our flow chart, asking ourselves at each step, what's the relationship, what's the relationship, what's the relationship all the way down until we end at a place with no more questions. Does that make sense? Okay. Do you guys want to try another comparison on your own? Yes. Okay.
Sorry, I can't get the Wi-Fi.
Oh, sorry. Mine's working.
I can see that.
Yeah, what I've experienced when it doesn't work is to close out of it. Like the iPad I have to run on the live network, the computer's cheating because I'm running on the school network.
Yeah.
A secret one. So compare 3 to 4. Do the same thing that we just walked through, but now on your own, compare 3 to 4. See if 3 to 4, what their relationship is. And I'll erase all of our arrows as we moved through it. And for the sake of people at home, I will pause the recording. I'm going to ask the same question again. Do they have the same molecular formula for the sake of the recording? No, they do not, which then means the relationship is that they are different. That's how we moved through. How do we see that relatively quickly? Okay? Theoretically, when you guys went through and did this, you came up with a molecular formula. What'd you get? C7H.
14.
Yeah, I agree. 14. 1, 2, 3, 4, 5. Dang, I don't think it's 6.
Yeah.
Well, that makes it even easier than I wanted it to be. So I won't go through the cheat quite yet. C6, what was the H?
14.
14 as well. So we have different numbers of carbons, so that very clearly doesn't align. Okay, so we'd call them different. What about the relationship? Well, none of the formulas there. It makes it obvious. Damn it. Because if we tried to do this, comparing 1 to 3, the H's don't align. So since we have the formulas, we can see that very quickly and effectively, efficiently, right? Makes sense? But what if we didn't have the formulas? Is there anything that would allow us to kind of get to that answer of them being different, recognizing they have different molecular formulas, without having to go through and painstakingly count every single hydrogen?
Would it be the carbon chain?
What do you mean?
Just kind of like identifying it?
I'm going to say no. We'll start with this. If we look at 2 carbons connected to each other, we have 6 hydrogens, right? What happens if I make a pi bond?
That's only 4 hydrogens.
I have to delete those hydrogens, right? Okay, so that would change the amount of hydrogen. So if I see a pi bond in one structure or one formula, I would need to see a pi bond in another one. Okay, pi bonds stand out. Those are obvious, right? Okay. What is a 2-membered pi bond? Well, really, all it is a 2-membered ring. Right? So when we delete those hydrogens, we have to do that to make a pi bond. We also have to do it if we're going to make a ring. Because if I had 3 carbons, and I now want to turn that into a ring, what has to happen? I have to delete those 2 hydrogens so that I can make that last bond. Okay? What we're referencing there is something known as saturation. A fully saturated structure has maximized the amount of hydrogens through our molecule. If it's unsaturated, we have to remove some hydrogens to replace those with a pi bond or a ring. Why is this helpful for me? When I compare structures 1 to 3, what do I immediately see in structure 3?
There's a ring.
There's a ring, which means in comparison to structure 1, what did I have to do? I had to remove hydrogens. Okay? So when I compare 3 to 1, immediately I'm like, those are different. They have different molecular formulas. Okay? I don't have to stack into it because I could add more carbons to make up the hydrogen differential, but then I'm adding more carbons and the carbons will be different from each other. Does that make sense? So if we understand a little bit about the connectivity and the patterns that happen when we change those structures, we can get different relationships coming out. Kind of make sense? So for this question, it becomes vastly easier if we have those chemical formulas. So if you feel it is necessary, then you should write down the chemical formulas as soon as you get the test or as soon as you encounter a question, because it does make it easier to see that different relationship. Okay? Kind of make sense? Okay. New example. Upper right-hand corner. What's the relationship?
I think they're identical, but I'm kind of guessing.
So, do they have the same molecular formula?
Yeah.
Yes. Are they superimposable?
Yeah.
Okay. This is a challenging question to deal with superimposability. It's playing games with our minds. We got to be real explicit with this. If we take a look at our carbon chain here, first carbon, second carbon is where our chlorine's connected, right? Okay. The angle of that bond is going up and to the right, correct? Take a look at the other one. Second carbon, chlorine, going left to right. That makes sense. The angle of that bond is going down and to the right. If I took this structure and tried to overlay it, do they superimpose? They do not. Okay, so what does that mean I have to do? I have to spin, flip, rotate one of those structures so that the carbon backbone can come into alignment. For me personally, what I would do is reference the far one on the right. And what I'm going to do is take that structure and I want to flip it over. The flip over I'm going to make is so that I can get my carbon backbone to align. So what I'm going to do is take this molecule and all I'm going to do is take it and do this. Everybody understand what I'm trying to do? Cool. Which people at home, sorry. Sorry, Linda. Okay. You're taking that structure with that chlorine. If we took our hand where the chlorine was, our thumb down, we're going to take that structure, we're going to flip it so that our hand is now aimed the other direction. Okay? Which means where's the chlorine connected?
It's still on the second carbon.
It's still that second carbon from the left. So that's phenomenal. We put our chlorine there, yeah? Okay? We have to be careful though, because this chlorine, well, actually before we even do that, now if we look at the carbon backbone, if we try to superimpose, does the carbon backbone overlap? Yes. So perfect. We have superimposability of the carbon backbone. We're starting to look at our structure in a proper orientation. But now we got to be careful with our chlorine. Where's the chlorine in our initial drawing?
Coming at you to the bottom.
It's coming at you. Okay? If we think through what we did, right? Okay. Like that. Does that kind of work? Coming at you.
Yeah.
What do? We took the molecule and we... Where's the chlorine?
It's going away from that.
It's going away, which means that chlorine shouldn't be shown as a solid line or a wedge. It should be shown as a dash. Now when I take that new drawing I've got and try and overlay it, the carbon backbone perfectly superimposes. I absolutely grant you that. Do the chlorines superimpose? No, they're aimed opposite directions. One's aimed out of the board at you, the other one's aimed behind the board. What does that mean? Are they superimposable? No. That puts us into our isomer category. Okay, kind of makes sense?
So if, say, the right structure was a dash, or both of the structures had just a solid line for the CL, then it would be?
So now we have an interesting question. Okay, I like that. So I'm going to add that question in here, but I want to change our drawings. If we just showed that as a solid line. Okay. Now are they considered superimposable?
Yeah.
No.
What?
Why not? What is the hybridization of that central carbon?
That carbon, sp2.
sp3. Why is it sp3?
Oh, because there's an H.
There's an implied hydrogen. Because that implied hydrogen, it is sp3. Okay, well, why does that matter? Is this a proper drawing of the molecule? No. Because that geometry should be tetrahedral. Each of those solid lines means they're all in the plane of the paper. If it's tetrahedral, that is not the case. So what you're now trying to do is compare two artifact drawings that don't accurately reflect the three-dimensional structure. It's not that they don't superimpose, it's that we don't know. There's not enough evidence to allow us to decide whether they superimpose or not. We have to draw our structure with the proper three-dimensional characteristics to allow us to make that decision. Does that suck? Abso-flippin-lutely. This is why we spend so much time talking about how we draw our structures, because the relationship between those structures makes a really big difference if we don't draw our structures correctly. Okay? Which I know stinks and that's painful and it sucks, and we'll talk about why that's important in a little bit. Okay? So back to this. If we clean that back up, what's going on? Well, we said they were not superimposable, so they're isomers. Do they have the same atom connectivity?
Yeah.
We've got the 4-carbon chain. At carbon number 2, I have the chlorine connected. Do I have the same atom connectivity? Yeah. Okay, all of the connectivity is the same. The other way that sometimes I'll reference atom connectivity is name. If you named this compound, there's 4 carbons, so it would be bute. They're all single bonds, so ane. And we have a chlorine at position 2. We'd call it 2-chlorobutane. How do we name this one? 2-chlorobutane. How do we name it? 2-chlorobutane. They're all 2-chlorobutane. If your name is the same, you have the same atom connectivity. Okay? Which does beg an interesting question. If the name's the same, why aren't they the same compound? That's because we haven't addressed all of our naming rules, and we need to add more naming rules so that we can differentiate structures like this. Right? And what we're looking at are now stereoisomers. This is where that name thing comes in. They have the same name. Right? This flow chart isn't fully complete. Right? And if we continue to study the special characteristic of that particular carbon, that's really what's coming out of this, is that that carbon has a particular bonding pattern that makes it special, that makes this issue manifest and appear. What we're referencing is the subject known as chirality. And what we're referencing with chirality is that you have two things that are non-superimposable, but they are mirror images. Your right hand and your left hand are mirror images of each other. If I put a mirror directly between my hand, they mirror across. But they are non-superimposable. And this is where everybody goes, well, aren't those superimposable? Remember, superimposability is all aspects must overlap. Okay? So when I do that, I'm saying the top of my right hand must overlap the top of my left hand while all the fingers align. And if I do that, my thumbs don't align. So your hands are chiral. They are non-superimposable and they are mirror images to each other. This is one of the things that hasn't shown up as a question yet, is that mirror image aspect. If you take a look at the chairs that you're sitting at, those are mirror images of each other, but they are superimposable. They would fit in the exact same space. So chairs are achiral. Hands are chiral. Why does that matter? If I give a chair to a left-handed person, is that going to cause any problems? It's a stupid question, right? If I give that same chair to a right-handed person, does that cause any problems? No. If I give a pair of scissors to a left-handed, and do we have any lefties in here? Oh, of course, it doesn't work so well when we don't have any lefties. If you give a pair of scissors to a left-handed person, you will probably see their face drop and they get angry at you. Why? Scissors are designed not for your butt, but for your hands. And your hands are chiral. So when you give a pair of scissors, particularly nice scissors, to a left-handed person, more than likely you're giving them a pair of right-handed scissors. They only work for right-handed people. The left-handed person now has to deal with this awkward thing holding on to that left-handed pair or that right-handed pair of scissors. Okay? And if you've never heard of or experienced that, find a nice pair of scissors. If you've got them lying around in your house, they're probably right-handed. Use your left hand with them. Okay? And if it's a nice pair, you will find that they are very awkward to hold. We've gotten a little bit better with technology, and we now try and design scissors that are ambidextrous, so they can be used by either hand, but it also loses some of the comfort that you get by having a handed set of scissors. Okay? Well, why do I care? Scissors aren't organic chemistry. It turns out that organic molecules have this same handedness, and when we consider the body, clearly our hands are chiral. All of the chemicals within our body also have a handedness with them. Okay? Well, why does that matter? Do we ingest drugs?
Yeah.
Yes. Those drugs are trying to react with the variety of handed molecules in our body. If we haven't considered the proper handedness, what happens to the effectiveness of the drug being able to link to where we want it to link? It doesn't. And we lose the effectiveness of the drug. Well, it's not that big a deal. We just design our molecules so they fit that handedness. That design is now reactions in chemistry and all that other stuff, which we haven't talked about. It's hard to get that handedness correct. Well, it's hard. Well, why don't we just ignore it? We'll just up the dosage, and instead of giving a person one pure handed molecule, I just give them 2 sets of scissors, right? And they can decide which scissor to use. Okay? That makes perfect sense, except what happens with that other pair of scissors that isn't getting used by the body?
A waste product?
It could just be a waste product. That's optimal. There's a lot of drugs that we have like that, where it's just a waste product. It could also be a magic set of scissors that goes through and stabs the person in the eye.
So toxicity.
The toxicity of that molecule could now have vastly unintended consequences. Okay? We were aware of chirality, I think I want to say Pasteur 1700s. Okay? So we knew about the chirality and the handedness of molecules. We didn't think it was a problem. It was about the 1950s when we discovered that it's actually a problem. Okay? How did we discover it was actually a problem? A lot of women had morning sickness when they were pregnant. We're like, let's build a drug that cures morning sickness. And they did. They built a phenomenal drug that cured morning sickness. It was handed. One of the drugs was right-handed, the other one was left-handed. The right-handed drug, phenomenal activity, shut down morning sickness perfectly. The left-handed thing didn't seem to have any consequences. So they didn't worry about it. They shipped it out to everybody and they let it run. Turned out the left-handed molecule causes birth defects. So however many months later, 8 months later, we're now seeing a massive wave of babies being born with huge birth defects. Okay? The very un-PC term described was flipper babies, because what ended up happening is it mutated the ability for the body to process limbs. And so they started losing limbs. Okay? They never actually fully formed. And it was all due to chirality, the handedness of our molecules. The handedness of our molecules that we initially said were identical. So it's not easy for the human brain to really see and wrap our head around. And if we draw it improperly, we lose all visibility on whether it's an issue or not. So what becomes important is that as we study chemistry and we look at drugs, particularly medicine, that what we're trying to do is pay attention to that chirality and ensure that we don't have unintended consequences of half of our system not doing what it's supposed to be doing. Okay? And that's why chirality now comes up as this big thing that everybody gets to study. Hooray! Okay? And of course, it's all 100% visual, going off of those 3-dimensional structures, which makes it very challenging to deal with because we don't work with 3-dimensional structures, we work with 2-dimensional structures, unless, of course, you purchased a model kit and have been manipulating the model kits to establish these relationships. Have we been doing that? That's where the challenge comes in. Kind of, sort of?
Yeah.
Okay. So, with that, yeah. Shouldn't have done that because I wanted to see where we wanted to start. Okay. Where we ended last week was looking at our Newman projections and our chairs. So we're going to rewind back a little bit, make sure we're okay with our chairs. Okay. The big conclusions that come out of this. Okay. If we go through and look at a cyclohexane, and the easiest example is just to pick a methyl cyclohexane. So we just add a methyl group on there. And if you remembered when we had our chair, we did the ring flip, and that methyl group went from being outside kind of the structure to underneath or above the structure. Those were 2 different energies. We don't see those energies manifest until we look at a Newman projection. So we'll add a CH3 on our Newman projection. Okay? If we look at that CH3, what we want to think about are now those Newman projections, those Newman energies. Do you see a Newman energy interacting with this CH3?
What do you mean a Newman energy?
What are our Newman energies?
Are you talking about the torsion thing?
Torsion is how we're switching in and out of our different Newman energy states. Right? But when we looked, if we went all the way back, we had our energy curve, right? Each of those wells was a Newman energy. or what I'm calling now a Newman energy. Do we see one of those Newman energies in this drawing? What's that? Where do you see the gouge? This CH3 next to this CH2. Whoops, as I draw it as a 3. That is a gauge interaction. Okay? And that's going to be the relevant one that we want to look at. Okay? There are other gauge interactions. For instance, that CH2 to that CH2. That's a gauge interaction. But those are atoms of the ring, meaning they're always going to be there. Okay? So they may be a higher energy state, but we're now just looking at how do we change off of that higher energy state. Does that make sense? Okay? We should also see a gauge interaction over there. Again, don't care because that's a 0 state. Okay? We're creating our baseline at that point. The one unique one that comes out of this is the gauge interaction being shown there. So what we want to go through and do is that ring flip. When we talked about the ring flip, what did I talk about doing? Anybody remember? The ring flip, we're talking about a chair. What are parts of a chair? The seat, the back, and the legs, and all those fun little pieces. Yeah. So when we're talking about our chair, really what we're concerned about, okay, is the back of our chair and the feet of our chair. And we're talking about a ring flip. What happens is I take the back, or what I call the head, and I turn that into feet. As I do this, I'm doing a sigma bond rotation. I take my old feet and I turn it into a head. That's a chair flip. Why is that going to be important? Where did the bonds go on there? Oh, I didn't put them on there. Okay. So what we want to do is now do that with our Newman projection. If I sat in this Newman projection, because it is still a cyclohexane, it's still a chair, but if I sat in that, where would I be facing? It's really hard to see, isn't it?
Yeah, I don't even
You see what I'm holding up to you? All I need is a yes, and that you can see the Newman projection. See the Newman projection? It's where my fingers are. Does that help? You're seeing this, the front and the back kind of stars. Got it?
I guess I'm
Stop looking at the board. Stop looking at the board. Just look at my Newman projection. Just look at mine.
because
Ignore
that
the
shows
board.
me that the CH2
I bet you to ignore the board.
Okay.
Ignore the board. Do you see my Newman projection?
Yeah.
You see it? Okay. Okay. And because this is why I'm saying ignore the board, because guess what I'm now going to ask? Do you see, is this Newman projection what is shown on the board?
No.
Do I need to get closer? Or you guys think you see it? Can you tell?
I can see it.
You can see it? Is it the same one as on the board? It's nuts. This is the same one as on the board. Okay. Got a lot of people saying no, and then some other people not actually venturing a yes or a no. That's okay. For those people that ventured a guess of saying a no, why is it a no?
The CH2s are in the wrong place.
The CH2s, so there's that CH2. Where's that CH2? Is it in front of the molecule or in back of the molecule?
That one should be in back.
I don't care what's up there. Is this one in front or in
Oh,
back?
in the front. Okay.
It's in front. Is it above the plane or below the plane of our ring?
Above.
Above. So when we look at our drawing here, we should expect to see a CH2 above and connected in front. Do we have that? No. Why not?
It's connected in the front and on the bottom.
Okay? Because you're looking at it backwards.
Yeah. Here we go. I feel better now.
Okay? You see it now.
Yeah.
We now have that proper Newman projection. Where's our methyl connected?
The front right.
Front right.
Yeah.
Okay, thank you. So there's our front right. Ta-da. So now we have everything that is shown here. I'm really trying hard not to drop this. Okay, are we good with that?
Yeah.
Okay. Real subtly, I'm going to take it and I'm just going to turn it. Do you see the chair?
Yeah.
Right? So now we're going to go back to our Newman. What did we say we needed to do when we did our chair flip?
Put the.
I guess it's my phone vibrating. Shut you up. Okay, again. There's our chair. When we do the chair flip, what do we need to do?
Rotate the center bond so that the feet turn into the head.
Okay, pause. Our feet turn into a head. Where's our feet? Left hand side or right side?
Your right.
My right, thank you. Okay, so there's my feet. I want to turn those into a head. I'm going to go back to the Newman projection. You see stuff like start to rotate a little bit? Everybody good with that? Okay, we look at it from the side again. What do we have?
Oh, canoe.
Sure.
What do you call it?
I call it a boat, but canoe's close enough. Same category. Okay, there's our Newman projection. So we said the feet, we would turn our feet into a head. What else do we have to do?
Head to feet.
We take our old head and we want to take that down, become our feet. Okay, I see what you're doing. No. Because you're looking at that. Why do we not look at that?
It doesn't really look like that anymore.
It doesn't look the same anymore. If we look, that front is now, what was that, like a Y? And if we look here, what is it? It's an upside down Y. As we did the Newman flip, all of those bonds rotate and we get a different view on it. Should I make you try and draw it?
I don't know about that.
Jeez.
You can make us.
Okay, so I can't hold it and draw at the same time, but we've got it roughly locked in view of what you're seeing. Okay. Put it out there so we can kind of look at it. So if we go through and do this, what I'm going to do is draw my Y's, right? That's a CH2. Okay, so that's just that front part. I then have and officially I guess I could draw those in red because we've been showing the front one in red. Okay, and then the back one is in black, right? And then we have the CH2 down low. You're making funny faces at me. You're not making funny faces at me, or you disagree with how I've drawn it? What's wrong with it? The order in which you draw it. Okay, so the order in which you draw it is highly personal. So if you feel it's easier to see the circles, draw the circle first and then do the rest. Okay, that is entirely personal in what you're seeing and how you're visualizing the molecule. And yes, do whatever you got to do, but that roughly is going to look like that. What I believe you're saying is that yours is going to look prettier than mine. That's okay. You disagree? No. Okay. Okay. All right. And if we finish this out, our black bonds, right?
CH2.
There there we go. We have to finish this all the way. Our CH3, which we're showing as this blue atom, is connected on the right-hand side. And it's kind of angled that up and away. So if we did that, here's our CH3. What happens to the rest of those bonds that I haven't labeled?
There's H's.
Those are all just H's. Goodish? Is that O because you just saw something? It just click? Yeah, that's good. Okay, cool. So now we've done our drawing. Why is this important for us? Oh, it's just an art class. It's just making me draw stuff to be difficult. We started this off with, what are the Newman energies in this drawing? Guess what we got to now ask over here? What are the Newman energies in this drawing? And when we now look at this, we're again referencing our CH3. And we're actually going to reference the exact same CH2. That CH2 is connected to the back, and that's down here. We're now looking at that relationship.
Now they're scattered.
Were they staggered in the first one?
No.
Yes, they were staggered in the first one. So staggered, right idea, wrong nuance. This is staggered gauche.
Anti.
This is staggered where those groups are now anti. They're as far away from each other as possible. Okay, what does that mean for us? Okay, because it isn't just, oh my God, let's just do goofy drawings. Anti versus gauche. What was the difference? And don't say the proximity.
Energy.
The energy. And in particular, the anti was
Lower energy.
lower in energy. That means this Newman projection is more stable. Lower energy. Okay. Do you really want to draw Newman projections every time we're asking about the lowest energy chair or the lowest energy cyclohexane? There we go. Green right away, I like it. No, God, no, please don't make me do that. Instead, what we'll go through and do is acknowledge the relationship between these, and we can reference that position versus that position by different names. Okay? In our gauche interaction, that CH3 is straight up. Officially, it could also run straight down. Okay? Up or down. That's effectively running on the axis. We'll call it axial. Our other CH3 is located kind of going out from the molecule. It can be out up or out down, but it's still going out from the molecule. We reference that one as equatorial. What does that mean for us? When I now to draw out a chair, I want to make sure that I draw the chair in such a way that my large groups are equatorial aimed. Okay? Does that matter? Yes. You all heard of glucose?
Yes.
You all heard of cellulose?
Yes.
Chemically identical. Does that seem kind of weird to you? Seems kind of weird to me. What's the point of glucose? Energy. Energy storage. Okay? We want to use our glucose. What's the point of cellulose?
Something to do with plants.
Structure. One is permanent, rigid form, do not move. One is, let's change this out so I can get some energy. Vastly different properties. Hugely different. But structurally identical. You want to know what the one difference is? Glucose has an axial OH. Cellulose has an equatorial OH. That's it. That's the only difference. Isn't that just nuts? I thought that was crazy when I learned that. And if you have to take biochem, they talk about labeling it. They add another naming system into it, of course, and you'll hear different references and worry about that later if you have to worry about it. Okay? But all you're doing is changing that one position from being more stable equatorial or less stable axial, and you get vastly different end results of those molecules. That's insanely nuts to me. Just whoop, 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 and that's it. Give me all the energy to don't touch me. Like, that's crazy. Kind of, sort of? Okay. So we're going to delete all that, make life miserable. I guess I should have asked first. Oh, well. What I would recommend you do, we don't have a whole lot of time before the exam, but it's a good idea to try and at least practice a couple of these, is to take these names and draw them out into the chairs to see how they would manifest. Okay? Okay? We're talking about Newman projections, so right away we have cyclohexane. So we've already given that as our skeletal structure. Okay? Other part of our naming, we're saying di and methyl, which means we have two CH3s somewhere on here. I can just pick one. I'm going to put a CH3 there for the moment. And it says di, so I need another CH3. I have to place it somewhere else around the molecule. Okay? Where do I have to place it? Well, that's going to be dictated based off of the locator. 1, 2. By definition, our first methyl group is at 1, which means our second methyl group needs to be at position 2. It doesn't matter the direction we number. Okay, so we could have put our second methyl group up. I didn't put it up because there's words in the way. There's our CH3. Okay, we should immediately be saying this is a problematic drawing per your conversation back with our chlorobutane. It's a problematic drawing because those are sp3 carbons, which need to be tetrahedral, which means I need wedges and dashes. How do I know whether they should be wedged or dashed? That's that cis thing out front. What does the cis mean? The cis means the methyls are on the same side. So if I define the blue one as wedged, what must the red one be? It must also be wedged so that it is now cis. Okay? When we now want to draw this into chairs, what we could go through and do is establish our chair, and we could now draw on our methyls. Where do we draw them on? It ultimately doesn't matter as long as you have your frame of reference for it. Okay? So I'm just going to randomly number 1, 2, 3, 4, 5, 6. Where do you want to put your blue methyl? 1, 2, 3, 4, 5, or 6? On the 1. Okay. The ones were arbitrary. It's just a labeling system so that we can communicate where to draw it. Okay? Officially, I did want you to put it there. That's why I numbered it that way. Okay? So we can put in our methyl. Okay? Well, now where should we put it? Should we put it here? Or should we put it here? Interestingly, there's only two places. I can't put the methyl here. Or here, or here, or here, or here, or here, or here, or here. None of those places are allowed. It's only the blue places. Why is it the blue places?
Because that's just how the structure
Ish. Those are referencing our equatorial and axial positions. Our axials are straight up and down. Which of those two positions is axial? That was kind of
the
dumb.
top one.
The one that,
The
yeah,
straight
the
one.
top one. Okay, the other one is equatorial. If I now want to put my methyl group onto this, my CH3, should I place it at the axial or the equatorial? Why do I want to place it equatorial?
It's more stable.
Why do I want to draw it more stable? Why do I want to draw it lowest energy? It's an easy answer. You're right. It's a really easy answer.
Could you sit still?
Close enough. It's what the question asks. The question says draw the lowest energy. Okay?
There we go.
It could have just as easily said highest energy, so we got to make sure that we're addressing what the question asked. It said we want its lowest energy, so we'll put our CH3 in that equatorial position. Which then means we now need to put the red one on in our drawing. Okay? If we look at our numbering system, we went 1, 2. Which direction are we moving around the ring? Clockwise. Which means when we start here at our 1, where's number 2 going to be? It has to be down here. Those are being like, well, can't I go that way? You've changed the direction you're moving around the ring. What you just drew was the enantiomer. And you're like, what the hell is that? Give me 10 minutes. Okay? What you're talking about there is the relationships between structures in that stereoisomers category, and it sucks. Okay? Maintain your count directionality. Okay? So this is position 2. Okay? Position 2, similarly to position 1, has an axial and an equatorial. The axial is straight up and down. Interestingly, the axial is going to be aimed straight down, not straight up. Talk about that in a second on the other structure, potentially. The equatorial is going to get aimed right there. Where do I put my methyl group? Why do you want to put it equatorial? It's lowest energy. Sophie, what'd you say? Because they're cis. Cis is what you were asked to draw, also in context of energy. This is where things are going to get really important. Where is this red CH3 aimed? Up or down? That is aimed up. Everybody see the angle it's aimed? It's aimed upwards. Those people being, well, why can't I draw it like this? Then it's aimed downwards. That's not a proper drawing. We'll address the proper drawing in a second. That's not allowed. Where that red bond is your choice. Where is our blue methyl aimed? Down. Your answer. Did we draw the lowest energy? Yes. Did we draw cis? One is up, one is down. Is that cis? No. We may have drawn the cis in our overhead view nicely, but as soon as we moved to the chair, we allowed our energetics to dictate what we wanted to draw. What we were being asked to draw was cis. What we drew was trans. One is aimed up, one is aimed down. That is not cis. That is trans. So what do we have to do?
Put one of those up or one of them down?
We have to move one of our methyls. I'm going to opt to move this methyl. Okay? What I've now drawn is the cis 1,2-dimethyl cyclohexane. This CH3 is now aimed down. That one's aimed down. This should be a little bit weird because what did we say they were? Here we showed them as wedges, which meant they were coming towards us. Theoretically aimed up. What did we do? We just took the molecule and we flipped it over. We looked at it from the other side of the page. So there is no up, there is no down until you've defined it. We defined putting the cis CH3 as down because we wanted equatorial. We didn't define it as up, as our drawing initially showed, because up would have been axial and that wouldn't have been as stable. Kind of make sense? As soon as you start to answer the question, you get locked into a viewpoint of your molecule. Okay? Until you start answering, all viewpoints are possible. As soon as you start, you're now locked into that particular viewpoint, and you can't change. Okay, first hand, then second.
For the chair drawing, those are just straight lines for the CH3s? They're not coming at you or away from you? They're just on
So up here, we had to define wedges and dashes because those were sp3 atoms. You'll notice down here, we aren't defining wedges or dashes on anything. That's because the chair naturally is a three-dimensional drawing. Okay? So if I draw a house, you might be like, well, that's two-dimensional. But if I draw a house, oof. I've not taken any art classes. Don't give me a hard time. I said, don't give me a hard time, you jerks. Okay? This is still a two-dimensional drawing, right? Is there three-dimensionality implied within it?
Yeah.
Yes. The overhead view doesn't have any implications of three-dimensionality, which is why you have to add wedges and dashes. The chair necessarily has three dimensions already drawn into it, which is why you don't need to add wedges and dashes. You do have to be able to interpret it, though, and that becomes a challenging question. If we were going to go from here to here, Where am I looking at the chair to get this?
I'm gonna say from the top.
If you were looking at it from the top, is the CH3 going towards you or away from you?
Away.
Away. And if it's going away from you, what would you draw it as?
A dash.
What did we define it needed to be drawn as? Wedge, which means we can't be looking at it from the top. We have to be looking at it from the bottom. You gotta love three-dimensionality with two-dimensional drawings. Kinda, sorta? Okay. So cool. What happens as we switch in trans versus cis? Does that change our relationships a little bit? Okay. Does it change when we change the numbering? Yes, it does potentially change our numbering as well. Okay. Here we don't get a perfect lowest energy. But if we switched it to trans, would we? Yeah, we would get a perfect lowest energy. Okay, so it depends on the name of the compound and where those substituents are located. Sorry, I forgot you.
Could you show this on the model?
Yes. Oh, God. Okay. So we look at the overhead view. Okay, and this is going to become a fun one. Where is this red one aimed?
Behind.
Behind. So if we were to draw the overhead view, we would draw the red one as what? Wedge or dash? Dash, because it's going away from you. Where's the blue one aimed?
Right. Side.
If we look at the overhead view, the things hanging off of the six-membered ring need wedges and dashes. If you say it's going off to the side, is that a wedge and a dash? No, which means you're not doing it right. Okay, that's because it's confusing. It is. Okay, we know the things hanging off must be wedged or dashed. When it's equatorial, it's very hard to see wedges and dashes. So look at the axial. Where's this one aimed? At you. That one would be wedged, which means that one must be dashed. Okay, make sense? So now how do we get it to the chair? There it is. Everybody see the chair? Okay, I guess I should be aiming at you because you asked. Okay, if we skew that a little bit, that blue atom is on that back spot, that back carbon. That's our back carbon over here. Okay, you'll note the CH3 is kind of aimed down and it is aimed out to the side, but it is kind of hiding behind stuff. Okay, not a good way to draw, not an easy way to draw it, but that's how we defined it. The red atom is at the feet of our chair. Feet of our chair aimed straight down. There it is. Everybody kind of see it?
Yeah.
We good? Is that sufficient for what you wanted? Okay. If we went through and did a ring flip, what happens? So there was our back, right? What should we do to the back?
Make it feet.
Feet. What should we do to our head?
Make it. Wait, what?
That's my feet. I lie down in chairs weird. Give me a break.
Head.
Come on, jerk. When we sit in our chair, now which direction are we facing? Oh, the other way. That's interesting. Okay. What happened to my red atom?
It's now equatorial.
Ooh, it was axial, but I go through a ring flip and it becomes equatorial. What happened to the blue atom? It was equatorial and it is now axial. As we do ring flips, we exchange axial and equatorial. Neat. Questions?
Can you show it from the other side of the top?
Oh, from the overhead?
Yeah.
So there's our overhead. Does the overhead show axial equatorial at all? No, it doesn't. The only way we'd see axial and equatorial or energy differences is going into a chair. Even then, the chair isn't showing us the energy difference. Newman projections show us the energy difference. But what Newman told us was that equatorial was more stable than axial. So the overhead view actually hides a bunch of information that we would not have any information about until we draw the chair. That's why we have to move through each of those drawings. Kind of make sense? Good follow-on questions.
And doing the flip changes the energy too, right?
It can change the energy depending on our chair. I didn't build this one as a very good chair. Okay? But as we do the flip, okay, what was equatorial becomes axial. What was axial becomes equatorial. So here we've got one stable interaction and one unstable interaction. When we flip it, what happens? The exact same system. But what if, of course you would do it that way. We swapped it to our trans system. They're now both equatorial. What happens when I go through and do a chair flip?
They're now both axial.
They're now both axial. Is there a difference in energy between the chairs? Yes. Okay. And that difference in energy manifests in reactivity and all sorts of other fun stuff that are probably beyond the scope of the class and you won't have to worry about again. Okay. The big lesson that you guys really want is dealing with glucose and the changes within glucose. Okay? So, what does this end up eventually getting us to us? This is now moving a little bit into chirality, which we'll talk about again after our exam next week, just because I don't think we're going to cover it as much detail as we kind of need. Okay? Thalidomide is the drug. Okay? That's the big drug that set everything off in the 1950s. Okay? So you're welcome to look at it. This squiggly line, okay, is referencing that stereochemistry. So that carbon right there is where the handedness appears. That carbon or that bond should be defined as wedged or dashed. Every other bond doesn't matter. All the other bonds are perfectly okay. That single bond, whether I make that a wedge or a dash. Wedged cures morning sickness, dashed causes mutant babies. That's a pretty significant difference. Okay? This does manifest in other drugs as well. I want to say naproxen, I think. If you look at naproxen, I think there's an R naproxen and an S naproxen. And when you buy it, it actually says on the label R or S. Okay? That's a nomenclature system referencing this wedge and dash thing, which we'll kind of talk about in a little bit. So the big deal, we talked about our chirality, our chairs, achiral, our hands, chiral. Mirror images, superimposability. That's the definition behind those. But when we look at a molecule, how can we look at a molecule and quickly say whether it was chiral or achiral? That's not quite as trivial as we would like it to be, okay? But there is a bit of a cheat, okay? That bit of a cheat is right here, okay? If we have a carbon that has 4 distinct things bound to it, it has a handedness. Because if I have 4 different things bound to it and I put a mirror image on, we see those mirror images? This mirror image, there is no orientation. I can't spin, flip, or rotate that molecule so that it superimposes on this. Okay? That's referencing the definition of chirality. It is non-superimposable on its mirror image. This is where it manifests. If we have a carbon with 3 different things bonded to it, okay, where 2 things are the same, I could spin, flip, or rotate that so that they do superimpose. That molecule is achiral because it is superimposable on its mirror image. Only when it is not superimposable on its mirror image do we insert this chirality aspect. Okay? The simplest case that we need to be worrying about is that if we see a carbon with 4 distinct groups connected to it, that is going to introduce a handedness that we have to be aware of. Okay? So your cheat with chirality is finding that asymmetry point, and that's finding a carbon with 4 unique things connected. Remember when we talked about being familiar with structures? This is why when we look at this, we should be able to quickly say that that's the only spot with 4 unique things connected to it. The double bonds immediately drops it to 3 things connected. Just 3 total things, not even 4 bonds. There's only 3 groups. So all of those carbons are ignored. That carbon with a double bond, ignored. That carbon with a double bond, ignored. Nitrogen only has 3 bonds, ignored. Double bond, ignored. Nitrogen, 3 bonds, ignored. Double bond. Carbon, 4 bonds, but 2 of them are hydrogen. I can't tell the difference between the hydrogen, so I don't worry about it. 2 of them are hydrogens. Can't tell the difference, so I don't worry about it. This carbon is connected to a nitrogen. Carbon, can I tell the difference? Nitrogen and carbon, yeah. One N versus C, yes. Okay. Implied hydrogen, NHC and C. Ooh, can I tell the difference between those 2 C's? Said another way, can I tell the difference between one C and another C? Some people are saying yes, but I think you're saying yes because you're looking at the drawing. That's okay. C versus C, there's no difference. It's a C.
Yeah.
So it's just a letter. Can you tell a difference between that carbon and that carbon?
Yes,
Why?
because of the.
Because it's connected out to something else. So that difference does not have to manifest at the atom. It can manifest a step further away. How far away does it have to manifest? As long as it manifests, they're different, period. Okay, so that carbon is a chiral center. That's where we'd have to be concerned about this handedness and dealing with those wedges and dashes. Okay. This is where we would break down our stereoisomers into 3 new categories. I know I'm real close to time and you're freaking out. You're not responsible for knowing these definitions yet. Okay. Enantiomers are fitting our full chiral definition. Structures that are non-superimposable and are mirror images. Diastereomers are structures that are non-superimposable as well, but are not mirror images. Okay? The diastereomer definition sucks. Ultimately, what it comes down to is it's not enantiomers. If you get to a system where you're like, these 2 structures, are they mirror images of each other? No, they're diastereomers. They're the catch-all leftover. Mesos are a real special case of identical. We'll look at a few probably again after the exam, but those are kind of the hardcore definitions behind them. Okay? What I want you to be able to see is that we're adding to our flowchart. Here's our stereoisomers. The next question we ask is, does it have a chiral atom? Because if it has a chiral atom, that's where we're now starting to branch into geometric isomers, cis and trans, which we know about already, which weren't on our list. Okay? Or we now branch into differentiating between enantiomers and diastereomers. And our difference there is mirror images. Most students will immediately go through and just ask the mirror images question or the superimposable question. All of the questions have to get asked as we move through the flowchart as we deal with these. Okay? If we think back to those 2 structures where we had the non-superimposable carbons, you guys remember that? Chlorine, those 2. We ended at stereoisomers. Do we have a chiral atom? Yes. That carbon is chiral. It's connected to chlorine, carbon, hydrogen, and carbon. Can I tell a difference between my carbons? Yes. One's a CH3, one's a CH2. That is a chiral atom, so yes. Now deciding, are they mirror images of each other? Do you all see the mirror image? I'm going to take this molecule and I'm going to flip it over. You just have to trust me that I'm flipping it over. When I flip it over, it was dashed, but I'm taking the molecule and I'm flipping it over, which then means it's... You all see the mirror image now?
Yeah.
So that mirror image is not an easy thing to necessarily see because you're typically locking it into the structure as drawn. You have to realize you have to spin, flip, rotate to see all of those potential alignments. Okay? Does that suck? Hell yeah, that sucks. Okay? Okay? It sucks enough that even in second semester when I see questions or even if I was taking any tests, I saw a question asking about these terms, I would skip it and move on. Because it's not worth my effort, because I know mentally I have to fight through all of those alignments, and that's not easy for me to do. Okay? Is it something you're responsible for? Yeah. So get that question wrong, don't worry about it. Kind of make sense? Okay.
So there's not gonna be too much about this on the test.
Nope, definitely not too much on this test. The next test you might see a few more questions, but this test I think there's one that pushes down into stereoisomers as a classification, and there's one that's acknowledging that those two structures that I had drawn up there and I now just deleted were both called 2-chlorobutane. They had different arrangements or different orientations of atoms in space. I have to have a different name. What is that different naming system? This is RNS. Okay? I don't want you to be able to define what is R and what is S for the exam on Thursday. I want you to be able to look at it and be like, that carbon right there needs to be designated RS. You just need to be able to point to it and say, or circle it and say, that spot needs an RS label. Okay? How do we know it needs an RS label? You have a carbon connected to 4 different things. Does it have to be carbon? No. Will it be carbon? Yes. It's okay. Kind of, sort of?
Yeah.
Okay. These slides we will again go through again at the beginning of the next unit, just to kind of review the content so that I can actually ask questions about it on the next exam. For this first exam, it's just kind of being aware of the problems that we don't want to have to face. Okay? With that, I got to be done.